we want to find the equation of the curve that passes through the point. I'm going to change that to 0, comma, -2. Yeah, that'll be fine, I think. And whose slope at x comma y is x times y. So they've told you a differential equation here, they just haven't written it mathematically. But it's all this last part right here, whose slope at the point xy is x times y. All of that is just saying that we want the slope at a particular point. So the slope dy dx should be equal to x times y. That's all they're saying. Great, we can solve that separable differential equation. So now we're going to solve it. So I've got dy dx equal to x times y. I want my x is on the right and my y is on the left. So that's going to be 1 over y times dy equal to x times dx. We're going to integrate both sides. So the integral of 1 over y dy equal to the integral of x dx. We're going to get the natural log of the absolute value of y is equal to the antiderivative of x, which is x squared over 2 plus c. And we typically do put the plus c on the side of the independent variable. Right? Since y is a function of x here, we're going to put the c on the x side. It's almost always the case. And then we're going to solve for y. So we're going to say that e to the natural log of the absolute value of y is equal to e to the x squared over 2 plus c, which becomes e to the x squared over 2 times e to the c, which becomes a times e to the x squared over 2. And in this process, you end up taking care of whether or not y is positive or negative. So we can just say that y without the absolute value is equal to a e to the x squared over 2. Wow, it looks really terrible, James. Sorry about that. So that's our general solution. But then we also have the initial condition that when x equals 0, y equals -2. So then we plug in y equals -2 and 0 for x, and we get -2 equal to a times e to the 0 squared over 2. 0 squared over 2 is 0, e to the 0 is 1. So we end up getting that a is equal to -2. So then we can write our particular solution as y equal to -2 times e to the x squared over 2. But honestly, I think the hardest part about that problem is recognizing what those words mean, right? They're saying, oh, the slope at the point xy is x times y. That means dy dx is equal to x times y. And the rest of it is pretty relatively straightforward as far as solving a differential equation. Yeah. It could be on either side. But the reason I want to put it on the x side is because I know that I'm trying to solve for y as a function of x. So I might as well make my life easier and put less things on the y side to begin with. But really what's actually happening here, when you do this, technically what you're really doing is you're saying, I'm going to have a c on both sides. Like from here, I would really have the natural log of the absolute value of y plus a constant equals x squared over 2 plus a constant. But then we can bring them all to whichever side we want. I want to bring them to the not y side. I'm going to rewrite this as the natural log of the absolute value of y equals x squared over 2 plus c2 minus c1. But then we're going to call that a new constant c. So we're kind of just skipping all those steps and jumping straight to where we want to be. Cool. Other questions about that? Okay. Yeah, we probably, so I know people said in the reflections they'd like to see more Euler's method and other things. like differential equations, but we also should stop about let's talk about Euler's method for one more example, and then we will move on to this 3D graphing and vector stuff. So Euler's method. Sorry, this is 1 second. Where's my, there we go. So here's what we're going to do. We're going to use the method to estimate y of 3 given the differential equation y prime equal to x plus y and y of 1 equal to, let's say 0, with a step size of 0.5. The numbers might be terrible. They usually are in Euler's method. So we don't have to draw anything, but in fact, we probably will, after we're done with this, we probably will draw the slope field just because this one's not terrible to draw. And there's something I should say about it, but let's do this part first. So we know that we're trying to find, and I'm going to graph this to kind of think about what's happening here. So I'm given that y of 1 is equal to 0. And I'm trying to get over to what happens when you plug in 3. And I'm going to take step sizes of a half. That means it's going to take me 4 steps to get there, right? I have to plug in, I have to do 1.5, 2, 2.5, and then finally 3. So on my 4th step, that's when I should be finding my approximate value for whatever y of 3 is. All right. So I'm typically going to call this y sub 0. That's my first one. And then I need 4 more steps. So y sub 0, that's when x is equal to 1. And then y sub 1 will be when x is equal to 1.5, and so on and so on and so on. I guess I could write them out here. And finally, my y sub 4, we're going to get when x is equal to 3. So I have to go all the way to y sub 4. I like to think ahead about what I'm doing here, right? It's good to kind of think, okay, that's where I'm going to end. So it's always the same. I probably have memorized this formula at this point because I've just seen it so many times. But honestly, I'm not thinking about the formula when I'm writing it down, right? I know that my next y value, I could probably put this here. So my y sub 1 is going to equal my previous y value plus my step size, my run, times my slope. That's really what I'm thinking about here. So then we do the usual thing. Most of the book calls this f of x comma y. That's your slope at whatever point you're plugging in. So then my y sub 1 is going to be my previous y value, which is 0, plus my h, which is always going to be 0.5, times my slope, which is going to be f of my first x and y coordinate, 1, 0. So let's say my slope is going to be 1 plus 0, which is 1. So y sub 1 should be 0.5 times 1, which is 0.5. Cool. I don't really think I need to record the x values because every time the next x value is just an increase of 0.5. So I could point out, I guess I've already written it over here, so I might as well. So when x is 1, y is 0. When x is 1.5, we're approximating y to be 0.5. And then we're going to do it again. So y sub 2 should be the previous y value plus my run times my new slope, which is going to be, I guess it is, so I take it back immediately. It is good to record the x and the y value so that you know what you're plugging into your y prime, your differential equation to get your next slope. So it's going to be f of 1.5 comma 0.5, which is going to be nice. We're just adding those together. So we're going to end up getting 0.5 plus 1/2 times 2. So that's going to be 1.5. Keep going. y sub 3 is going to be the previous y value plus always the same step size times f of my previous coordinate, which is going to be 2 comma 1.5. Things might start to get a little bit messy here. That's going to be 1.5 times, or sorry, plus. The nice thing about this particular differential equation is you're literally just adding the x and the y coordinates. So you can really just add those together and say, oh, that's 3.5. And then half of 3.5 is 1.75. That's going to be 3.25. And then lastly, y sub 4 is going to be 3.25 plus, again, 0.5 times f of my previous point, which was going to be 2.5 comma 3.25, which is going to give me 3.25 plus to 5.75. Half of 5.75 is 2.875 plus 3.25 is 6.125. I think that seems right. Close enough. So that's our estimate of y of 3 given this differential equation with this initial condition. Okay. It's kind of it's really tedious. It's pretty tedious, but it's very doable as long as you I really think though, memorizing the formula is not helpful. Like you can, it just if you don't know what you're doing, it's hard to actually remember where all the numbers go in the right place. But if you think about what you're doing, then it's just your previous y value plus your run times your slope. I think it's relatively reasonable to kind of work this out and just get it. So that's what I would say about that. I guess we could draw the terrible slope field. I really don't like doing it, as you might have guessed by the tone of my voice. Let's do it anyway, because there is something to see here. So our differential equation was y prime equal to x plus y. And when you're trying to identify a slope field, you really kind of want to find like the lines typically or curves more generally where all the slopes are the same. So for example, we're going to set y prime equal to different values. So if y prime is equal to 0 is almost always the first place you're going to look, then we're going to get x plus y equal to 0, which is going to be better written as y equal to negative x. Or just solve it for y. So we know that along the line y equals negative x, all the slopes are going to be 0. So I start drawing this thing. Sorry. Oops. Chords. What is your problem? Why is this chord so terrible? I don't know why this chord is so terrible, to be honest. Try it again. Plug in the other one. Nope. Okay, fine. You're just terrible. For some reason I just don't like the other chord as much. I don't know why I'm biased against the VGA chord versus the HDMI chord, but I am. Maybe because it has a million things attached to it. Screw this thing on. Sorry for the delay. You guys should start drawing this thing. Take the right one here. Okay. Plug it in. Screw it in. Don't screw it, it won't stay. Ah, these technical difficulties. Okay, that should be good enough. Plug it in. Press the button on the thing. Have weird purple colors. Why is it purple? Uh, because it's not connect. There we go. Okay. Just don't touch anything over here. All right. So let me put that back over there. Why? What? Okay. You have to way over there. Technology. Isn't it grand? Sorry. Okay. And then I'm sharing my screen again. Sorry, 1 second, person on Zoom. There you go. Why is the screen why are there 3 screens? Okay, that's bizarre. Anyway, we'll do that. Okay, everyone can see things. Don't touch your computer. So what I'm saying is We want to kind of make some marks here. So 1, 1. It is kind of nice to make like little points in space here. Like in every kind of integer pair, you might plot the dot. Just to make it easier to draw the rest of the stuff. So there we go. Good times. So what I was saying is, along the line y equals negative x, the slope is always 0. So here's my line y equals negative x. I can say, great, 0 slope there, 0 slope there, 0 slope there, 0 slope there, 0 slope, 0 slope, 0 slope. Relatively quick. And then if I go one bigger here, y prime is equal to 1, then I'm going to know that x plus y equals 1, or y equals negative x plus 1. So along the line, y equals negative x plus 1, so the same line just shifted up 1. Now the slope is always going to be positive 1. So positive 1, positive 1, positive 1, positive 1, positive 1, positive 1. We can keep doing the same thing. If y prime is 2, again, I picked a especially easy example probably. It doesn't get much easier than y prime equals x plus y if you want both variables in there. But we can still kind of do this thing for whatever you've got. Pick constant values here and then find the curve that slope is occurring on. So if I have x plus y equals 2, that's going to become y equals negative x plus 2. So on the line, y equals negative x plus 2, which is just another 1 up. Now my slope is 2. So it's going to be a little bit steeper. 2, 2, 2, 2, 2. And then I think we can see the pattern here. Whatever I'm picking for y prime is essentially my y-intercept of my line. So if y prime is 3, I get y equals negative x plus 3. So along this line here, my slope is even steeper. Whoops, it didn't look steeper though. Sorry. I'm not good at drawing slopes steeper than 2. And then steeper than, so this one's going to be 4. Wow. Yeah, good job, James. And then 5. And then 6. Sure. And then in the other direction, if y prime is negative 1, then you get y equals negative x minus 1. So it's this line here. And that slope will be negative 1, which is going to look like that. And then if y prime is negative 2, we're going to get x plus y equals y prime, or y equals negative x plus y prime. So y equals negative x minus 2. So we just go down one more, and then our slope is, oh geez, negative 2. Sure, like that, like that, like that, like that. And then the same pattern is persisting. We go, the further down we go, the more negative the slope is. If y prime is negative 3, we're along the line y equals negative x minus 3, which is this line here. And it's going to be a slope of negative 3 on all those. And then the next line down is going to be a slope of negative 4. The next line down is a slope of negative 5. And finally, negative 6. Might be the best one I've ever drawn. Give myself a round of applause there. I'm very pleased with this. I won't lie. It looks better than I thought it was going to look. So that's a decent way. Again, if your differential equation is not too terrible to deal with, it's definitely much worse if you have like x squared or y squared. Then finding the curve is a little bit more work than just a nice straight line. But for something like this, it's not too terrible to draw the slope field. And then if you wanted to, you could then say, well, if we started at our initial condition of y of 1 equal to 0, which is right there, right there? Yeah, x is 1, y is 0, right there. And we try to follow, so if we follow this for like half a step, and then follow that for like half a step, and then follow that for half a step, you can kind of imagine getting to our value of 6.125. Seems not implausible. Kind of cool. I don't know. Kind of. It's all right. Where are the things I put down over here? Not over here. All right, we need to spend some time talking about the 3D. I don't want to touch these chords. The 3D graphing stuff. And yeah, the 3D graphing stuff. The 3D graphing. So 3D graphing and vectors. So 3D graphing, how much do we need to know? Some, not hopefully too much. Ooh, angles already. All right, well, we'll see if we can get there. So for the 3D graphing, there's kind of a few shapes you should know about, but really mostly it's like planes and spheres. So here's our 3D graphing system. I usually draw it like this, where you have your Y and your Z axis on the paper, and then your X axis is like coming out at you. Like that. If I'm thinking about it like in physical space, if I'm looking at that corner of the room, this room is not like perfectly square over here, but that corner, if I imagine that corner is my origin, then this line here is my y-axis, that line there is your x-axis, and this line here is your z-axis. That's what I'm usually thinking about when I'm visualizing this. So if I wanted to plot like a point in space, so like the point 2, 3, 5, we're going 2 in the x direction, so 2 towards you, 3 to the y in the y direction, so 3 to the left, and then 5 up. And you can kind of do that in any order you want. The way we often do this is by drawing the box that has the point you're looking for as the corner opposite the origin. So I need my red pen. So what we're going to do is we're going to first go 2 in the x direction. So there's the point 2, 0, 0. We don't need to label all these points, but it helps. From there, we're going to go 3 in the y direction, meaning we're going to travel in a direction parallel to the y-axis. Just like in 2 dimensions, if I asked you to find the point 2, 3, you would go 2 in the x direction, and then you would go 3 in the direction parallel to the y-axis, also known as up, to get the point 2, 3. This is especially important in 3 dimensions because when you travel parallel to the x-axis, you have to make sure you're really traveling parallel to the kind of slanty diagonal direction that the x-axis is drawn in. So that's why we usually do the x direction first. So then from there, I'm going to go 3 in the y direction. And really what I'm actually going to do is I'm going to go that way. I went too far. And then from the y point that's 3 over, I'm going to go 2 in the x direction, parallel to the x-axis. So right there, there's my point 2, 3, 0. Here's the point 0, 3, 0. And then to be kind of, and mine doesn't look super parallel, I gotta admit, it's kind of not the best. From here, I might go up 5. And then from this point here, which is 0, 0, 5, I might go over 3. I don't know why I'm saying might, I'm definitely going to do it. So there's the point 0, 3, 5. Same deal for the x and the z coordinate. I can go either up from x or in the x direction from z to get the point 2, 0, 5. And then finally, putting it all together, this point over that way in the y direction, or from this point moving in the x direction, or from this point moving in the z direction, I end up with the point 2, 3, 5. And since we're going this direction anyway, hot direction. So since we're moving towards talking about vectors anyway, we might as well point out that if you wanted, you could draw the vector. There's like 3 different notations for vectors that are used. I am partial to this one using slanty brackets, or there's a different word for those. Using brackets that look like that. Wow, and maybe drawing your 3 better. So there, you can draw that as the vector v with an arrow on top of it equal to 2, 3, 5, or you could write it as 2, 3, 5 as a column vector. You could also, I guess, the other notations are terrible. You shouldn't use, I really don't recommend using notation like this. That's not great, although sometimes used. And anyone seen anything else? Hopefully the answer is no. Hopefully you haven't seen any other notations, except for one. There's one other notation which I do recommend, which is the IJK notation. You can also write this as 2i plus 3j plus 5k. Where I, j, and k are just the unit vectors or vectors of length 1 in each of the x, y, and z directions. So really what this really means here is this is 2 times the vector 1, 0, 0 plus 3 times the vector 0, 1, 0 plus 5 times the vector 0, 0, 1. That's what the IJK notation means. It's just another way of writing the same vector. So we will definitely we'll cycle through all of them. Really, yeah, all of them. They all get used for various reasons. I know we're kind of jumping ahead here, but it seemed like a good opportunity. So we'll still talk about other things, but I'll point out that we can also find the length of this vector, the length, or better word, magnitude of the vector v equal to 2, 3, 5 is just how far it is from its initial point to its terminal point. So the initial point drawn, so this vector is drawn in the standard form, meaning, or standard position, meaning it's starting from the origin, which is how we would love to draw every vector if we could, because it's nice. And it also makes it easy to find the distance between the initial point and the terminal point. Because you want to find the distance between 2 points, it's just going to be the square root of the difference in the x values squared, plus the difference in the y values squared, plus the difference in the z values squared. But when you're starting from the origin, those initial points are just 0, 0, 0, so you don't really need to write them. So we can just think of the magnitude of a vector as the square root of the sum of the squares of the components. Which in this case happens to be what? I don't know. The square root of 4 plus 9 plus 25 is 38. This vector has a magnitude of the square root of 38, or a length, which is the square root of 38. Okay, but I'm jumping ahead. There's still more 3D graphs to talk about, so let's not get too crazy with the vectors yet. So what else can we talk about graphing wise? We can graph some planes. I want to graph the plane z equal to 4. What I would say about most of the graphing things we do with 3 dimensions is they're very analogous to 2-dimensional things. So like if I was to ask you to graph instead in 2 dimensions, the line y equal to 4, we know what that looks like. There's your xy axis, and y equals 4 looks like this, where y is 4 and x can be anything. In the same sort of way, if I want to graph the plane z equal to 4, well, I'm going to go up 4 and then move as much as I want, forwards, backwards, left, right, or in any direction in any xy direction. So x and y can both be whatever we want. So if we try to graph this, and again, we're kind of limited here, but if I try to graph z equals 4, I'm essentially just going to go up 1, 2, 3, 4, and then say, okay, great. From that point there, I can go as much as I want in the y direction, as much as I want in the x direction. I can go left, I can go right, I can go forwards, I can go backwards. So I'm getting a whole plane's worth of points. And eventually you have to stop drawing because you can't draw forever. So you can think of like, oh yeah, there's my plane that is 4 above the xy plane. Sorry, my plane's kind of not the best looking. That's the idea. If you're missing variables, just like in the line y equals 4, you're missing x, which means x can be anything. In the plane z equals 4, if you're missing x and y, it means x and y get to be anything and everything. Which also means that if someone asks you to graph something like yeah, y equals x squared, well, it's not just a parabola, because what variable is missing here? From my x, y, z coordinate system, z is missing, which means you can move in the z direction freely. So first we're going to draw the two-dimensional curve that we have. So I'm going to draw y equals x squared. So this is my y-axis. This is my x-axis. So y equals x squared is going to be a parabola. It looks like it's kind of opening to the right because, right, we open up on the y-axis. So here's my parabola opening up on the y-axis here. But then I can move as much as I want in the z direction. I can essentially go up as much as desired. Or down as much as desired. So what we essentially have is something that looks like this, right? It's a parabola, but it's like a sheet, which is called a parabolic cylinder. I don't know why they chose the name cylinder for basically if you take any curve in two dimensions and extend it in like a third dimension, you call it a cylinder, even if it's not cylindrically shaped like we would classically think. So this is a parabolic cylinder. In the same sort of way, if I was going to graph something like x squared plus z squared equal to 9, well, that equation certainly looks like the equation of what sort of two-dimensional shape? It looks like a circle. I'm gonna, yeah. So I'm trying not to lose all my, I put papers everywhere. My God. Okay, sorry. Trying to lose everything here. Yeah, it looks like a circle, but we can extend that circle in the y direction. So first I'm going to draw this circle in the xz plane, which is kind of a pain in the butt. So this is a circle of radius 3. So be careful when you're drawing if you're drawing along the x-axis, right? If you take something that's a certain length and then you tilt it towards you, forced perspective means it looks smaller. So in the x-axis, our tick marks need to be less far apart than on the other axes. So like if I'm drawing in the z direction, like that's a length of 1. In the x direction, they shouldn't look that long. More like this. And then down 3. So we're going to hit there, hit there, hit there, and I'll go back over there in a second. And I'll just say some people are better drawers than others. I'm okay. I've had a lot of practice and I'm still just okay. So then we're going to go as much as we want to the left or to the right. Usually just kind of pick one direction though. So it's more like your classic cylinder, right? It's actually cylindrically shaped. Yeah, x squared plus y squared, x squared plus z squared equals 9. Y can be anything. So a cylinder of radius 3. All right. Probably the shape we are the most interested in talking about is something like the sphere of radius 2 centered at the point 4, 0, -3. They don't really want to draw. I could draw it, but it's not going to be very informative for me to draw a sphere just somewhere in the middle of space. What I really care more about is finding the equation of the sphere. And just like a circle, we have the same sort of format. So I'll point out that this equation here, x plus 1 squared plus y minus 5 squared equal to 16, is the equation of a circle centered at the point -1, +5 with a radius of the square root of 16, which is 4. And this is really true of a lot. I know I said this already. I'm going to say it again. A lot of three-dimensional things, you kind of just like, add on an extra coordinate and then say it's good. This is especially true when we talk about linearizations of functions of two variables later on. So later on, I know in 17a, at some point, someone should have talked about linearizing a function or finding the equation of the tangent line. I had like this L of x thing equal to f of a plus f prime of a times x minus a. Don't worry, we'll talk about it again when we get there. I don't remember if it's, I think it's a 17c thing. So, but later on in 17c, when you talk about linearizations of functions of two variables, it's going to be like the exact same formula. You're just going to add on another piece for the next variable, and it's going to look like exactly the same ones, which is kind of great. The same thing is true here. If I want to find the equation of a sphere, I'm just going to add on another kind of thing for the z coordinate. So instead of being x plus 1 squared plus y minus 5 squared equal to the radius squared, it's going to be x minus 4 squared plus y minus 0 squared plus z minus negative 3 squared equal to the radius squared. And really, this is all because of the distance formula, right? When you're trying to find the equation of a sphere, you're really trying to find an equation for every point on this surface, and all these points have one thing in common. They're all the same distance away from the center. So you could, although I don't really want to, I really want to write this the nice way as x minus 4 squared plus y squared plus z plus 3 squared equal to 4. I will point out that if you took the square root of both sides, and I'm going to do it even though I don't want to, you have that the square root of x minus 4 squared plus, I'm going to write it this kind of gross way, y minus 0 squared plus z minus negative 3 squared. Sorry, that looks terrible. I hate when I do that. Equals 2. Or in other words, the distance between the point 4, 0, negative 3 and any point x, y, z is 2. The radius. That's exactly how you describe every point on a sphere. There, my center is right there at the point 4, 0, negative 3. This is my good old sphere here. What you're saying is literally any point on the sphere, right there, x, y, z, back there, x, y, z, anywhere you like, every point on the sphere is the same distance of 2 from the center. That's exactly what this is expressing. But then we don't like writing it like that, so we square both sides and write it like this, because this looks much nicer. And then, of course, we like to make it harder for some reason. They say, great. Then find the center and radius of the following sphere, given by the equation x squared plus 2x plus y squared minus 6y plus z squared plus 8z equal to 7. The radius is not the square root of 7. To be able to find the radius and the center, we have to rewrite this in the standard form, where you have x minus something squared plus y minus something squared plus z minus something squared equal to some number that is the radius squared. And to do that, we have to complete the square. So, and usually, I probably wrote this in the nicer way. People often write this where it's like x squared plus y squared plus z squared plus 2x minus 6y plus 8z minus 7 equals 0. So your job when you see something where you have x squared plus y squared plus z squared, those three things have to have all the same coefficient, preferably 1. But if the coefficient isn't 1, but they're all like 3 or 2 or 7, before you do anything else, just divide both sides by that coefficient, even if it means you're going to get some terrible fractions. We'll do one next. Yeah, we'll do one next. So we take this and then we write this as x squared plus 2x plus blank plus y squared minus 6y plus blank plus z squared plus 8z plus blank equals 7 plus blank plus blank plus blank. Because if you add something on the left, you better add it on the right. And then to find the things we add, you take your coefficient of the thing that's to the first power, divide it by 2, and then square it. So 2 divided by 2 is 1. 1 squared is 1. Negative 6 divided by 2 is negative 3. Negative 3 squared is 9. 8 divided by 2 is 4. 4 squared is 16. So then the reason we've done that is because each of these three things, the thing with the x's, the thing with the y's, and the thing with the z's, each becomes some quantity squared. This is going to be x plus 1 squared. This is going to be y minus 3 squared. This is going to be z plus 4 squared. I'll point out, the number you get inside the parentheses is always going to be exactly half of whatever you had there. Half of 2 is 1. Half of negative 6 is negative 3. Half of positive 8 is positive 4. Always works that way. On the right-hand side, I miscalculated. That's okay. It doesn't really matter. 7 plus 1 plus 9 plus 16 is 33. Yeah, 33. I think, right? 16 plus 9 is 25. 26, yeah, 33. Okay. I was going for 36, but I miscalculated. So the way I got those was I took the coefficient of x, of y, and of z, cut them each in half, and then squared them. But this added stuff on the left, I also had added on the right. And it's true, right? X plus 1 squared is x squared plus 2x plus 1. Y minus 3 times y minus 3 is y squared minus 6y plus 9. Z plus 4 times z plus 4 is z squared plus 4z plus 4z plus 16, which is z squared plus 8z plus 16. Yeah, this is not that. It's a totally different thing. Yeah, sorry. That's why there's a little line around it, right? Because it's different. Yeah. Yeah. So then we can finally say that our center, and the way I always think about the center, is just the values of x, y, and z that make the left-hand side of the equation completely zero. So x has to be negative 1, y has to be positive 3, and z has to be negative 4. And then the radius is equal to the square root of 33. Let me ask you a question, which might sound like a dumb question, but I'm asking anyway. Is the center of the sphere a point on the sphere? No! It doesn't satisfy the equation. If you plug in the center, you get negative 1 plus 1 squared plus 3 minus 3 squared plus negative 4 plus 4 squared, which is equal to 0. Is that equal to 33? Definitely not. Just like the center of a circle isn't a point on the circle, the center of a sphere isn't a point on the sphere, or doesn't satisfy the equation, which is totally fine. It's not supposed to. It's still the most important point of the object, even though it's actually not a solution to the equation or a point on the object itself. That's true for other things as well. So the center of the sphere, most important point of the sphere, not a point on the sphere. Yeah, we can do one more. Vectors. No, I want to answer those vector questions first because those ones actually, the angles are reasonable to deal with. So let's talk about those vectors real quickly. Looks like I'm going to change all of them. So let's say our vectors are A equal to 0, negative 6, B equal to 4, negative 4. Yeah, no, I like negative 4, positive 4. And C equal to, oh yeah, sure, root 3. 5 root 3 comma 5. That's the worst notation I've ever seen, James. Holy shit. 5 root 3 comma 5. And they ask us to find the length of each vector and the angle that it forms to the positive x-axis. Cool. So if only one of your components is not 0, then that vector is just however long that is. So that vector that starts at the origin and goes 6 down and looks like this is how long? 6 long. It's not negative 6 long. Our lengths have to be positive, or not, I should say non-negative really. The way you can find the magnitude of A is the square root of the sum of the squares of the components. And the square root of 0 squared plus negative 6 squared is the square root of 36, which is 6. But if you just have one non-zero component, it's just the absolute value of that non-zero component. But we knew, right? We started at the origin, we moved 6 down, it's 6 long. The other two are a little bit not as easy. So for B, and so then the whole point of these questions is the angle should be relatively obvious. So you shouldn't have to do anything special like use a dot product yet, although we will do that in the future. This angle measured from the positive x-axis is 270 degrees. In a similar way, for B over here, I'm going 4 left and then 4 up. If I was in the first quadrant going 4 over and 4 up, my angle would be 45 degrees. Because along the line y equals x, the angle is 45 degrees. This angle here looks like it's 90 degrees plus another 45 degrees, which is 135 degrees. The magnitude, well, I'll point out the magnitude, you're really just using the Pythagorean theorem. Right, you're really just saying that the hypotenuse of this right triangle, whose base is -4 and whose height is +4, you're saying, great, -4 squared plus 4 squared equals the hypotenuse squared, and then you're square rooting both sides. You're saying, oh, it's the square root of the sum of the squares of the components of the vector. And I suppose over here, I should have thrown, I'll point out, this is not an absolute value. I know it looks like an absolute value, but when you put the absolute value symbol around a vector, it's called the magnitude or the norm or the length. It's not the absolute value. So here, the magnitude of the vector B is equal to the square root of 16 plus 16, which is the square root of 32, which you could simplify as 4 root 2 if you wanted to. Cool. The last one's definitely the hardest one. So we're going over 5 root 3 and up 5. So we're going farther right than we are going up. So we'd expect our angle to be less than 45 degrees because we're going more in the x direction, less in the y direction. So we're going to go, I don't know what 5 root 3 is. Let's say that's 5 and that's 5 root 3. We want to find that angle there. Okay, well, this is where you might need some trigonometry. So what we know is that this point here is the point 5 root 3 comma 5. And I know that this side is 5, this side is 5 root 3. I guess we can find the magnitude first. The magnitude of the vector C is the square root of 5 root 3 squared plus 5 squared. We're almost done, I promise, which is the square root of 25 times 3 plus 25, which is really the square root of 4 times 25, which is 2 times 5. So then pick whichever trig function you like the best. I'm going to pick sine. And I know that sine of this angle, according to my triangle, should equal 5 over 10, which is 1/2. And I know that the angle whose sine is 1/2 is pi over 6, but we're talking degrees, not radians, so 30 degrees. And yes, your teacher does expect you to know that.